Record. Okay. Okay, good morning, Dr. Nat here. Let's continue with yesterday's topic. So I was talking about binomial distribution and also Poisson distribution. So the difference between these two distribution is that Poisson is actually an extension of binomial. And in a sense that Poisson deals with large sample size where the n is super large and the probability is very, very small. So for binomial, the condition was that it has to be 5% from the total population for the binomial to be great. But for Poisson, they just want the n to be very, very large and the p to be very small. And basically it follows whatever condition that the binomial distribution has. Okay. And then this one, we discussed about the equation for Poisson, which was, where was it? Was this equation? Okay, so if random variable x has Poisson distribution lambda, where the lambda is the mean, if they are talking about the average or they are talking about the mean in the question, it refers to the lambda. Then x is a discrete random variable whose possible values are non-negative integers. Again, you only have positive integers as your random variable. If you have a negative value, then the Poisson distribution will only result in 0. So the parameter lambda is a positive constant. The probability mass function is given by this equation. We have seen this equation yesterday. It was e to the power of minus lambda, lambda to the power of x divided by x factorial. Okay. And e is just 2.718. You have it in your calculator. Don't remember it. And I have good news as well. I double checked on the syllabus and I am allowed to give you guys the equation during the exam. So what are the equations that I will give you? Let's see. Because there's a lot, right, for this topic. So it depends on what is in the appendix of the textbook. I need to go to the end of the slide. Give me a minute. Oh. Come back, okay. Now it's hanging. Come on. I need to show the appendix. Yes, finally formula. I was also scared because I can't remember all the formula as well. So I was asking to all my colleagues whether I can give it or not. Let's see. Hello, it's stuck. Oh no. Great. Oh, okay. Okay, so I will be giving, oh no, is it not here? Oh, it's here, okay. So let's take a look. Okay, so this is what I'm going to give you. We have the uniform distribution, the mean and the variance. And this is just the section in the book. I'm using William Navidi. No, sorry, this is Douglas C. Montgomery textbook. It's in your info course. Binomial, you have this equation but this one you have to memorize how to expand the combination equation. We've talked about this one before. And then we have the geometric we're going to cover today. And we have the Poisson, which is this guy over here. And the mean is just lambda, and it tells you where in the book you can find it. Okay, and we're going to deal with something new today as well. So yesterday we were talking about Excel, right? And I wanted to emphasize on you guys understanding the parameters of the Poisson. So from the Excel, I ask you to write down how would you write it in the math formula. And then from the formula, kejap Hilman, and then from the math formula, you will be able to use something like this. And we will cover, give me a minute, okay. So this is also in the textbook. And did I write where it came from? I have it somewhere in the slide, don't worry. So you don't have to use your calculator. You don't have to like punch in the numbers. You can actually see here that over here that this is the equation for cumulative Poisson probability. And for the cumulative, your x goes up to 3, for example. And if your mean is, let's say your mean is 0.6, so the cumulative distribution function for Poisson is 0.997. So you don't have to use your calculator. You can just refer to this table. So this is why the Excel by default uses the cumulative distribution function, because the textbook also uses the cumulative distribution function table to solve the problems. Okay, so you won't have the normal probability mass function PMF. You only have CDF, which is cumulative distribution function. So you need to know how to use this table, and hopefully we can do that today. Okay, so I have a bunch of questions in the chat. Doctor, this one is from which book? Sorry, I didn't hear it. Okay, so I have it in the slide. I wrote it down somewhere. Give me a minute. Okay, and the slide is going to be available to you guys. Okay, so for the equation, this is in table 1 in Appendix A, Douglas C. Montgomery textbook. Okay, I'm going to show you the textbook in a bit. And then for the formula, I have it written down in our examples. Okay. So here, use table A.2 in J.L. DeVore textbook. So you don't have to bring your textbook during the exam. The sheets, the equation, and also the cumulative distribution function will be given. This is just for your reference if you want to look at it yourself. And again, I use all the textbook that is in the info course. Not all, I think 3 at most. So this is what I'm using. Let me share my screen. Oh, I'm scared to share my screen because it will disturb my iPad. I'll share it at the end, okay? I'll share the textbooks that I use for this class at the end of class. And I think I've gone over this before, but it's okay. I'm going to tell you guys again. Hopefully everyone can pay attention now, because I had someone asking me what textbook I use one day before the exam. Not a good plan, guys, okay? All right, so let's continue with our exercises, and hopefully we can get to geometric distribution. Okay, so we already covered this one, which was very, very confusing in my opinion. So hopefully the examples coming after this slide will be much better. Okay, so we talked about Poisson distribution having a mean of as the concentration. The concentration is the mean, which is the mu. So let me try to write on this iPad. I'm not used to it. Okay, so mean is the concentration. Okay, so whenever you have something that is, for example, in this case, it is particles per mil. And for other cases, flaws per centimeter. Or other cases such as, you have units over units, basically. Units over units. This will be your concentration. And that would be your mean for your Poisson. And let's try to look at an example. Hopefully this makes better sense. This makes much more sense. Okay. For the case of a thin copper wire, suppose that the number of flaws follows a Poisson distribution with a mean of 2.3 flaws per millimeter. So this is our mean. So let me write that down. Mu is 2.3 flaws per millimeter. Okay, so now it's asking us determine the probability of exactly 2 flaws in 1 millimeter of wire. So remember we had Poisson equation was, we want to know what is Px of random variable x equals to 2, and this would be e to the power of minus lambda to the power of x over x factorial. Now our x is 2, and they're asking for 1 millimeter of wire. So let X denote the number of flaws in 1 millimeter of wire. We need to know what is the total number of flaws first. Remember, this is our mean. It's not the total number of flaws. So let X denote the number of flaws in 1 millimeter of wire. Then EX is 1 millimeter times 2.3 flaws per millimeter. So you get 2.3 flaws. So now your lambda is 2.3. So you just substitute that into the equation. Okay, so that is e to the minus lambda 2.3, 3 to the power of 2, which is the x that you want, right? And then divided by 2 factorial. So this is the answer. So here we can't use the cumulative distribution function because this is just x equals to 2. But if we have x less than 2 or x less than 3, then we can use the table later. Okay, so moving on, determine the probability of 10 flaws in 5 millimeters of wire. So they've given you the initial concentration, right? But this concentration will change depending on the question. So this is your like initial starting point. Let's just see that. Okay, so B, determine the probability of 10 flaws. Now X is, we want to know what is X equals to 10. Okay, so now the mean will change because now we're dealing with 5 millimeters of wire. Now we're dealing with 5. Previously, we were talking about 2.3 per millimeter. So this was the initial condition given to us. So B is going to be, our mean will be 5 times 2.3 per millimeter, which is going to be 11.5. So this will be our new mu. Okay, hopefully no one is confused. And then our px equals to 10, e to the power of minus 11.5, 11.5 to the power of 10 divided by 10 factorial. Okay, again, you can't use your CDF for this one. You have to use your calculator. Okay, so C, determine the probability of at least 1 flaw in 2 millimeters of wire. Again, this is not dealing with 1 millimeter. We have to find the new mean. So the new mean will be 2 millimeter times 2.3 per millimeter, which is 4.6. So this will be our mean, the new mean based on the condition of the question. So now our P is X greater or equal to 1, which is, we can't use the CDF if it's going to be greater than 1 because 1 goes up to infinity. So we need to rephrase this question and write it like this: 1 minus Px equals to 0 equals to 1 minus E. Okay, so this one, they already simplified it, but it will be basically E to the minus 4.6, and then you have 4.6 to the power of 0 divided by 0 factorial. Again, you need to know what 0 factorial is. It's just 1, and this would be also 1. So this is why this equation is only e to the minus 4.6. You already simplified it. So this is your answer. Oh, sorry, we can't use the table yet. Okay, so did everyone understand this part? I mean, this example? I mean, I think it makes much more sense compared to the previous slide. Basically, what I'm going to recap this slide again. Basically, it's giving you the concentration. Typically, we would use the concentration as our mean, but we're not dealing with 1 millimeter. We are dealing with various lengths of the wire. So we have to calculate what is the mean for the total length of the wire. Just like before, we were talking about 10 particles per mil. Remember this one? So this was our initial concentration. But when we're dealing with a volume of water, which is not 1 mil, so you had to find out the new mean. Okay, so it depends on your V. This was yeah. So this is like your number of flaws. If we're trying to relate to the current example, number of flaws, and this would be the probability. So the probability would be 1 over the V. And the number of flaws is the concentration times with the length of the wire. Okay. Just trying to relate that. Okay. So hopefully more examples we can try to make sense of this better. Okay, so next example, particles are suspended in a liquid medium at a concentration of 6 particles per mil. So we have our concentration. Let me just write it as con so that we're not confused. 6 particles per mil. Okay, a large volume of the suspension is thoroughly agitated and then 3 mil are drawn. Okay, so it didn't give us the total volume, but we're talking about 3 mil now. So I want to know what is my new mean. So that would be the number of water drawn, right? 3 mil times with 6 particle. Oh, I like my handwriting on this iPad. Okay, so 3 mil times 6 particle per mil. So the mil cancels out. So I would get 18 particles as my new mean. Okay, that's not a good handwriting, by the way. Okay, so what is the probability that exactly 15 particles are drawn? So now we're talking about the probability of X equals to 15. And we have our mean as 18 or our lambda as 18. So we can't use the table. We have to use our calculator for this one. E to the minus 18. And then we have 18 to the power of X, which is 15. And we have 15 factorial. Okay, so that is your answer. Use your calculator. I'm not going to do that. So let's see if we got this right in the solution. Okay, so this is the same equation that we had. Okay, so hopefully everyone gets this example. Any questions so far? Is everyone okay? All right, so no questions. Okay, great. So if you have any questions and you're shy to ask in the class, you can type it in the chat box as well. So what would happen if the total volume was just 3 ml? What would happen if the total volume was just 3 ml? Can we withdraw exactly 15 particles? Okay, so let's try to look back at the question. So it was saying to us, particles are suspended in a liquid medium at a concentration. It's giving us the concentration, but it didn't tell us what the large volume is. So let's say we have like a huge basin over here. Let's say it's 1000 ml, probably. It's giving us the concentration, which is 6 particles per ml. So whenever we withdraw an amount of water, we would approximate or we would guess what is the number of particles in the water that we withdraw based on the concentration, right? Because we have that information. But now it's telling us what would happen if I have a smaller basin and this basin only, no, we can't use a basin for this. Wrong. So I have a syringe. What was it? Did someone say something? Wow, this syringe is very beautiful. Okay, so this syringe is 3 ml, right? And we know that the concentration in this syringe of water or liquid, whatever, is 6 particles per ml. Still 6 particles per ml. So if I put all of the water inside this syringe in a cup of water, in a very small cup of water, can I withdraw exactly 15 particles? Can we find the probability of that? What do you think? This is a discussion, by the way. No right answers. Well, there is a right answer, but I won't penalize you. Any guesses? No guesses? Everyone's totally confused at this point? Okay, so let's take a look at the water. So please abandon this basin of water. We're just dealing with the syringe. I told you that the water inside the syringe is 3 ml. And the concentration of the particles in the water is basically 6 particles per ml. How many particles do I have in 3 ml of this water? How many total particles?
18.
It's here. How many total particles do I have?
18.
18, correct. So can I find the probability of getting exactly 15 particles if I take all of this water inside the syringe? Yes or no? The answer is no, because when I have 3 ml only and I take all 3 ml, I will basically get 18. There's no running away from it. This is why the Poisson distribution only works if n is very, very large. Remember that. And you have to take a sample from a very, very big population. This is your sample. No, wait, this is your sample that we're taking from the basin. The sample has to come from a very large amount of water. You can't have a small amount of water and you say, okay, let's just take all this small amount of water. Let's do a Poisson distribution on it. You can't do that because it's very, very small. Not a good idea to have a distribution on a very small data. So when you're doing your projects, you have to have a lot of data. Don't be lazy and take a lot of surveys, okay? Okay, Nick Shazwan also said 18. Okay, great, thank you. So does that, do you understand what I was talking about when I said we can't choose 15? We can't find out the probability. Did that make sense?
Yes, doctor.
Yes, because 3 ml will have exactly 18 because I already told you the mean or the concentration was 6 particles per ml for this syringe. Therefore, 3 ml would have 18. If I take all 3 ml, I would get exactly 18. I wouldn't get 15 because where would the 3 particles go? It will stay in the air. You eat it? No, you can't have it like that. Okay, so moving on to the next exercise. What time is it? Okay, during a laboratory experiment, the average number of radioactive particles passing through a counter in 1 millisecond is 4. What is the probability that 6 particles enter the counter in a given millisecond? Okay, so it's giving us the average number of radioactive particles. And it's asking us what is Px equals to 6. So what is my mean here? What would be my mu? Anyone? Should I call names? It's easy question. What is the mu here?
4.
4. So let's write that 4. Okay. So e to the power of minus 4, 4 to the power of 6 divided by x factorial. So our x is 6. Okay. So this is the answer. Okay, so now the solution, let's look at the solution. The solution is telling us that we can also find the probability for something, for example, x equals to 6, using the CDF, cumulative distribution function, by doing it like this. So you have your x from 0 to 6, sorry, from 0 to 6, yes. And then you have your x from 0 to 5. So when you subtract this guy, what happened to my pen? If you subtract this guy with this guy, you would get exactly x equals to 6, even though it's CDF. So basically, we can also use this for our previous exercises. Okay, so let's try to look at the table and try to understand how to use it. Okay, let me remove this first. Okay, everyone, please pay attention. What we are trying to find, what is the CDF for mu of 4? Okay, mu of 4, and our x is 6. CDF. Okay, so let's look at the table. Mu of 4 and x of 6. Okay, mu of 4. Mu of 4, so we are dealing with this one. And x of 6 is going to be your x. So it's over here. Mu of 4, x of 6. So it's 0.889. And then the next equation, the next term was x from 0 to x equals to 5, right? So the mu is basically the same, which is 4, but the x is going to be 5. This is your second term over here. So 889, 785. 889 minus 785. 889, 785. Okay, can someone please remember that? 889, 785. Okay. 889, 785. 889, 785. Where is it? So this is going to be 0.889, 0.785. And if you minus these two numbers together, you would get the answer for x equals to 6. So this is how you use the table. But for you to use the table, you have to know how to rephrase the question in terms of CDF. So let's try to do that more in the next exercises. Does everyone understand how to use the table? Or was that too fast?
Yes, we understand, doctor.
Okay. So if you want me to repeat any parts, let me know, okay? Okay, continuing to exercise number 6. 10 is the average number of oil tankers arriving each day at a certain port city. The facilities at the port can handle at most 15 tankers per day. Okay, so we have our average number, which is 10. 10 is our average number each day. So you have your units here. Let's write it. So average. What is it? 10 tankers per day. Okay. The facilities at the port can handle at most 15 tankers per day. So that's your limit. What is the probability that on a given day, tankers have to be turned away? So what is the probability that on a given day, tankers have to be turned away? It already told you that at most, it can handle 15. What X are we dealing with? What is the probability that we are trying to find here?
Greater than
What is
15.
X greater than 15? X equal and greater than 15 or X greater than 15?
Greater than 15.
Greater than 15. Okay, so let's try that. So if I wanted to find out what is X greater than 15, how do I rewrite this so that I can use the table?
1 minus less than 15.
1 minus less than 15. Less than or less than and equal?
Less than and equal to 15.
Less than and equal. Okay, let's try that. So probability of X being less than or equal to 15. So let's try to find this one using the table. Hopefully we got this one right. Don't know. Oh, there's the solution there. We can cheat, but let's not cheat first. Okay, so our mean was 10. So let's go over here. This is our mean. Oh, my face is, okay. Okay, so that's the mean. And we want to find less than or equal to 15. So going down a bit over here. So this is what we're dealing with. So it would be helpful to have your ruler for this, or you can just write it across like that. So 15 is our X, and remember this is CDF, our cumulative distribution function, and our mean is 10, so 0.951. So let's go back to the question. 0.951. Okay, 0.951. So that would give me something. Let's see the solution. Okay, so this is how they rephrase it, exactly as how we did it. the CDF goes from 0 to 15 and 1 minus 0.951. Here, it's only giving you until 3 decimal places, but for the solution, it's giving you 4 decimal places. But you just use whatever table that is given to you, so don't worry about that one. So this is your final answer. Yay, I think we got it so far. Okay, moving on to exercise number 7. Does anyone have any questions so far? No questions? Okay, I'm going to continue. So exercise number 7, in a certain industrial facility, accidents occur infrequently. It is known that the probability of an accident on any given day is 0.005. Infrequently means it doesn't happen often. So the probability is very small, great. This is what Poisson strives for. And the accidents are independent of each other. Very important too, for your trials to be independent and have a constant probability. Remember, our binomial, our Poisson has to have Bernoulli type of trial, which is independent of each other and has a constant P. Let me write that down somewhere. I don't think it's in this slide. Trials must be independent and have constant P, constant P for success. Because you can't have a probability that keeps on changing, then the distribution won't work. Okay. So what is the probability that in any given period of 400 days, there will be an accident on one day? Oh. And then the next one is, what is the probability that there are at most 3 days with an accident? So let's try to figure out what probability they are trying to find here, or it's already in the solution. So the first one, what is the probability that in any given period of 400 days, there will be an accident on one day? So X equals to 1 lah. So here, this is our P. And this is our X. So we have to find out what is the mean. So the mean would be the mean for 400 days. Remember, we had an accident on any given day is 0.005. And for Poisson, it was NP. Remember this equation? So 400 days times with the probability. So you would get 2 as your mean for 400 days. Your mean changes depending on the question. Even though they've given you like the initial condition, you have to find out based on the given volume, given length, given days. So next one is, what is the probability that there are at most 3 days with an accident? So here they're using the same mu, I believe. So it is still number 2. And for X, it is asking for at most 3 days. At most. So 3 is the largest number. So X is less than 3. At most 3 days that are their probability. So X is less than or equal to 3. There are at most 3 days. 3 days and less. Okay. So B is talking about X is less than or equal to 3. So let X be a binomial random variable with N equals to 400 and P equals to 0.05. Thus, NP is 2 using the Poisson approximation. So it becomes easy now. This one, we are missing the 1 factorial over here. They simplified it for us. And this one is using the CDF. CDF of X less than 3. So let's look at the table. 0 to 3, the mu is 2. Let's use the table. Mu is 2, X is 3. Okay. Mu is 2, X is 3. Wrong one. Sorry. Mu is 2, X is 3. This guy, 0.857. Okay, hopefully you guys know how to use the table now. We already done 3 exercises using the table. You can try it yourself with the exercises, the textbook. Okay, 0.857, which is what we got from the table. Okay. All right. Okay, give me another 7 minutes before we end class. So exercise number 8. Oh, we can't cover geometric. Oh, but geometric is very easy. Let's try to speed up a bit. So exercise number 8, in a manufacturing process where glass products are produced, defects or bubbles occur occasionally, rendering the piece undesirable for marketing. It is known that on average, 1 in every 1,000 of these items produced has 1 or more bubbles. What is the probability that a random sample of 8,000 will yield fewer than 7 items? So it's asking you about x equals to 7. We're talking about items here. So we need to know what is the new mu. 1 in every 1,000 has 1 or more bubbles. So we're dealing with 8,000. So 1 over 1,000 items. This is going to be our mu times with 8,000 items. Defected item. Okay, so we would have 8 items with defects or bubbles. Okay. Oh, it's already here. Okay. So hence, if X represents the number of items producing the bubbles, we would have Px less than 7 because it's asking us fewer than 7 items. Okay, fewer. So it's not equal to 7, less than 7. And again, they are using the Poisson distribution. First, they tried to write it as binomial. For binomial, we're talking about N and P. P is 1 over 1,000, N is 8,000, and X goes from 0 to 6. But of course, we can convert a binomial distribution into Poisson distribution to become X from 0 to 6 with a mu of 8. And I would think the Poisson is more easy because we can just use the table. For binomial, you have to use the equation. Okay, so last one before we go to geometric, let's go for the table. What was our mu again? Mu is 8 and we are finding X of 6. Okay, mu of 8, X of 6. Mu of 8. Okay, so this is your mu and X of 6. Let me use my highlighter. X of 6. No. Okay. Mu of 8, X of 6. Where's my pen? Hello, come back. Okay. Mu of 8 and X of 6 would give me this guy, 0.313. Okay, that's the last example that I'm going to use the table, and let's go for a geometric next. Yay, the same. Okay. Oh, not there yet. Okay, so this is a yay. We're done with Poisson. Let's move on to geometric distribution. Okay, so in a series of Bernoulli trials, independent trials with constant probability of P of success, I already have it in here. Let the random variable X denote the number of trials until the first success. So when we were talking about binomial and Poisson, we were talking about what is the probability of X being exactly 15? What is the probability of X being exactly 6? So that was our situation with binomial and Poisson, right? But for geometric, they want to know how many trials does it take until you get the first success. Okay, so how do I say this? Okay, let's go for the multiple choice. Would that be a good example? Let's just go with the example that I have here. So if X follows a distribution of geometric distribution with a parameter P, which is our probability, then the probability mass function of X is given as P times 1 minus P to the power of X minus 1. So you have two parameters here, two variables, which is your X, of course, your random variable, and also your P. For Poisson, it was mu and X. For binomial, it was N and P and also X. Okay, so the mean for geometric is 1 over P, and your variance is 1 minus P over P squared. Okay. Moving on. So one exercise before we end class. In a certain manufacturing process, it is known that on average, one in every 100 items typo is defective. One in 100 items. What is the probability that the fifth item inspected? So our fifth item inspected is the first defective item found. So the solution given here is let X be the number of trials required to produce the first defective. So now using the geometric distribution of X equals to 5 and the probability of P equals to 0.01, it was given over here. We have our geometric distribution 0.01 equals to P, 1 minus P, X to the minus 1. So your X is 5 minus 1, so you get to the power of 4. So this is very easy, just use your calculator. What would be the tricky thing with geometric? Nothing, I think, because you just have to find out what is the probability and what is the number of the trial before your first success. That is it. Oh, we have another one, sorry. Let's go for this one and then end class. At busy time, a telephone exchange is very near to capacity. So this is talking about customer service. So if you were an engineer trying to make sure that the communication is going smoothly at your company, so this would be where you apply it. So at a busy time, a telephone exchange is very near to capacity, so callers have difficulty placing their calls. So you as an engineer have to solve this. It may be of interest to know the number of attempts necessary in order to gain a connection. So I'm calling this customer service for like 10 times, and only at the 10th time I get to talk to the representative or the customer service, right? So this is not a good practice. So here they're telling us, suppose that we let P equals to 0.05 be the probability of a connection during busy time. So this is our probability. This is the probability during a busy time, not during off-peak. We are interested in knowing the probability that 5 attempts are necessary for a successful call. In my opinion, 5 attempts is a lot to deal with. And as a customer, I would not be pleased, right? But we have to know what is the distribution for this. So using the geometric distribution with A as 5, this is our X, by the way, and P as 0.05, so the probability of the customer having to call at least 5 times to get a phone call passed through to the customer service is given by the geometric distribution 0.05, which is 0.05 times 0.95. This is 1 minus P, this is P, and then this is X minus 1, which is 5 minus 1. So the probability of me making a phone call during the busy time and the 5th call would be the success when I can reach them is 0.041, which is very low, by the way. But okay, that's the question. Quite often in applications dealing with geometric distribution, the mean and variance are important. For example, in the above example, the expected number of calls necessary to make a connection is quite important. Okay, so that's the end of class. I'll see you guys next week. Take care, everyone. Have a great rest of the day. Bye-bye.
Thank you very much, Doctor.
Thank you very much.
Welcome.
Doctor.
Bye-bye.
Thank you, Doctor.
Thank you, Doctor.
Thank you,
Thank you,
Doctor.
Doctor.
Bye.
Doctor.